So in Chapter 6, we're going to spend a little bit of time talking about what are referred to as inner product spaces. So let's talk a little bit about a motivation behind why we care about inner products. Okay, so let's look at this triangle. We've got a triangle made up of a u vector and a v vector. Let's say that they're both have their initial points here at the origin. We're going to do this in R2. Go out to the point x1, y1, so we can just represent the vector as x1, y1. Same thing with x2, y2 here for v. And then I'm going to look at the difference between v and u, and actually that would be a vector that would start here at the point x1, y1 and point toward x2, y2. But in general, we would have that u is equal to x1, y1, v is equal to x2, y2, and then v minus u is the x2 minus x1, comma y2 minus y1. All right, so if I'm given those two angles, u and v, how can we find the angle between them? So if we remember a little bit of trigonometry, remember our law of cosines says that if I want to find this angle theta, then I can do the opposite side squared has to be equal to the a squared plus b squared, and then minus 2 times a times b times the cosine of the angle in between the a and b. Notice that if theta is 90 degrees, cosine of 90 degrees is 0, you would have a right triangle, and you have the usual Pythagorean theorem. So the law of cosines is actually just an extension of the Pythagorean theorem. All right, so let's just put this in terms of the vectors in the triangle we started with. Certainly the length of u, since we put the origin at the initial point at the origin, said that backward, we would have square root of x1 squared plus y1 squared. Same thing with v, except just with x2 and y2. Same thing with v minus u, except with just the difference of the coordinates there. So using our law of cosines, we would have this relationship. This was the opposite side of the angle between u and v, v minus u. So that's the length of v minus u, has to be the length of u squared, length of v squared, and then minus 2 times the product of the lengths times the cosine of the angle between them. Now let's just do a little bit of algebra. FOIL out both of the differences here, both of the binomials. Notice that when you do that, you've got an x1 squared and an x2 squared, a y1 squared and a y2 squared. You have the same thing on the right-hand side. All of those are going to cancel. So on the left-hand side, we're just going to have the minus 2 x1, x2, minus 2 y1, y2. The right-hand side is just a minus 2, and then the two lengths of the vectors that we talked about, and the cosine of the angle between them. So if we solve for the cosine of theta, we get this quotient. Now notice in the denominator, we have just the product of the lengths. In the numerator, we have this product, or a sum of products, I should say, where we have the product of the first two components and the product of the second two components. So we see this, pardon me, we see this in this expression that comes up when we try to find the angle between the two vectors. So this is one way to motivate why we care about the dot product. So as far as the dot product on Rn goes, we actually refer to the dot product as an inner product. So the Euclidean inner product on Rn, if we have two vectors in Rn, x1 out to xn, y1 out to yn, we define their inner product or their dot product as just the sum of the products of the components. So that's our definition. We have some properties that this particular inner product satisfies. Certainly it's commutative. The dot product distributes over vector addition. The scalar, if I put the scalar with the v, or put the scalar with the w, or put it out in front of the dot product, it doesn't matter. You get the same answer all three ways. The last one says that every dot product of a vector with itself is greater than or equal to 0, and the only way that the dot product of a vector with itself can be 0 is if you started with the 0 vector. All right, so let's go through these properties for the Euclidean inner product, and then we're going to generalize this to arbitrary vector spaces. So let's look at the proof of the last one, because the other three are straightforward. You just go through and manipulate the algebra and get it to work for those properties. So for 4 here, let's say we start with a vector v. Dot product with itself certainly just becomes the sum of the squares of the components. And certainly if I square a bunch of real numbers and add them all together, I get something that's greater than or equal to 0. So that proves the first part of property 4. All right, let's do the other one. So that the a vector dotted with itself is 0 if and only if you started with the 0 vector. So if we start with the 0 vector in Rn, which is of course just all zeros, then certainly the dot product with itself is 0. Let's go the other way around. If the dot product with itself is 0, then we would have the sum of the sum of the components squared would be 0. But again, these are all non-negative, and we're adding it together. So the only way this can happen is if each individual component is 0. The only way that you can get a sum of squares to be 0 is if each individual number is 0. When we're talking about real numbers here. So that means that all the components had to be 0, which means that our v had to be the 0 vector. Now what property 4 allows us to do, it allows us to define lengths of vectors. And we use this notation with what looks like a double absolute value bar. We call this the norm of a vector, or the magnitude of the vector. It's the square root of the dot product with itself. And this is exactly this form we had when we were talking about the lengths of those two-dimensional vectors at the beginning of the video. It's the square root of the sum of the squares of the components. Now again, this is the Euclidean inner product. Other vector spaces have other inner products, but they don't necessarily have to be what looks like a familiar dot product to you if you've done dot products before. And we can also define other dot products on the Euclidean vector spaces that aren't our usual dot products. And we're going to do examples of those in class, but let's look at this idea of general inner products and look at a specific example of a general inner product. So we start with a vector space, and this is just a funky notation for a function. We use pointy brackets, if you will, to denote the inner product of two vectors. So when I've got this comma in the middle, I'm going to put in two inputs. That's why it's going from v cross v. That just means we have two inputs, and what we get out is a number. Then we say that this pointy bracket thing is an inner product if it satisfies those same four properties that we talked about the Euclidean inner product satisfying. So it's commutative. It doesn't matter the order in which you take the inner product. It distributes over sums. You can pull a scalar out in front. And that same one allows us to define length or magnitude or norm. A dot product of a vector with itself is non-negative, and the only way it can be 0 is if we started with the 0 vector. So let's go through these for a specific example. Let's talk about the vector space of linear polynomials. So they would be functions of the form ax plus b. We're going to define an inner product, or a purported inner product. We need to prove that it really is an inner product. We're going to define a purported inner product here as product of the two polynomials when you plug in 0 plus the product of the two polynomials when you plug in 1. Let's see that this really does satisfy the axioms of being an inner product. So here's p of x, inner product of p and x and q of x. This is its definition. These outputs, of course, are real numbers, so I can multiply in either order. So I can swap around the p of 0 and q of 0. And the same thing with the p of 1 and q of 1. And then that would be the definition of the inner product of q and p. Let's go to the second property, which says that you distribute over sums. The inner product distributes over sums. According to the definition, we plug in 0 into each polynomial, multiply the results together, and plug in 1 into each polynomial, and multiply the results together, and then add. So we have p of 0 times the quantity q of 0 plus r of 0, and similarly for when we plug in 1. Now distribute the numbers, and then regroup where you have p's together, p's and q's together, and p's and r's together. Just rearrange. And then we notice that the first two terms really is the inner product for p and q, and the second two terms are the inner product for p and r. So it really does distribute over addition in this case. This one's pretty quick as well. If I have a constant times p of x, inner product with q of x, the definition says I would plug in 0 into the first polynomial, multiply it by when I plug in 0 into the second one. Same thing with 1. I have a factor of c, a common factor of c in both terms. I can pull it out. What's inside the parentheses, of course, is the inner product of P and Q. If I look for property 4 now, it takes a little bit more to prove it, but we can get through it. If I take a dot product of P of X, or inner product of P of X with itself, I would get P of 0 squared plus we have P of 1 squared. Again, we're dealing with real numbers here. When we do square a real number, we get a positive, add them together. We can't get negatives. It has to be non-negative. All right, now doing the if and only if. If we start with the 0 polynomial, which is the 0 vector in the P1, then when I dot product with itself, I get 0 because P of 0 and P of 1 are both 0. Go the other way. If the inner product is 0, then we have the sum of the squares of the components is 0. Again, we're adding two real numbers together, and both of those real numbers cannot be negative. So if I get 0 out, each of the individual pieces must be equal to 0. This would say, now remember, we're talking about linear functions. So this says that the line would have to pass through the point 0, 0, and the line would have to pass through the point 1, 0. Well, the only line that does that is the line that is just P of X equals 0, which again is the 0 vector. All right, so let's just do a quick example. And like I said, we're going to do more examples in class. So if this was a little quick or doesn't make much sense right now, we're going to do more of this in class. But let's say we start with these two linear functions, 2x plus 1 and minus x plus 3. When I do the inner product of those two together, remember first we plug in 0 for x, so I would get 1 times 3. Put 0 in for x for both of them and multiply. The other one says put in 1 for x, so I would get 3 here and 2 here. And when I add 3 and 6 together, I get 9. Remember I said that the reason why we care about property 4 is so that we can define a length function, a magnitude function. So again, the magnitude of a vector is defined as the square root of the dot product with itself. This is why we want to make sure it's non-negative. Now this says when I dot product with itself, I put in 0 and I put in 1 when I add them together. So when I put in 0, I get 1, so I get 1 squared. When I put in 1 into P of X, I get 3, so I get 3 squared, so I get square root of 10. So with respect to this particular inner product, the magnitude of P of X is root 10. Again, we'll do more of these examples in class, a couple of more proofs as well, and get a little bit more into why we care about inner product spaces.